All right, so I made a major statement last video that I kind of want to dive back into now because it'll lead us into this topic of dispersion. So I said that light changes speed as it goes from a vacuum to traveling through a material, largely because there's quote-unquote stuff in the way. So let's talk more about what exactly that means. So when we talk about bulk materials, bulk just meaning large macro scale materials, there are so many things that we can talk about. There's a whole field dedicated to this, fields of science and engineering. Largely the field of just solid state physics is dedicated to bulk materials or solid state materials. I want to take a quick moment to talk about what's inside that stuff that light has to travel through. So what light sees as it goes through the inside of stuff, if you will. Once we have a better idea of what light is dealing with as it makes its way through materials, we can understand why dispersion happens. We can also understand retroactively why it might slow it down. So all textbooks at this level of physics will simply just state what dispersion is and ask you to accept the phenomenon without any notion as to why it happens. But in my opinion, it's actually quite simple to understand why, and so this is something that I'm giving to you, is this little extra bit of understanding instead of having you memorize just what dispersion is and moving on. So let's try to understand why. The definition of the term dispersion will come out as we go. So when light travels in a vacuum, no material, it travels at the speed of light, c, 3 times 10 to the 8th meters per second. When it hits a material, however, it may run into atoms of that material that it has to interact with. Consider a single photon of a certain wavelength, say cyan, and I'll try to get it in cyan actually, with wavelength around 492 nanometers. All right, so say we have this photon and it's traveling. Oops. All right, those are all supposed to be periodic. So matter is, of course, made up of atoms, which are actually quite spread out when you get onto this level of photons. And so as this cyan photon travels through a material, it still is traveling through the vacuum of space between atoms most of the time. So there may still be atoms around it, but the odds of it hitting one of these atoms is quite little. And the scale, of course, is not even close to correct, but it gives you the impression of what I'm talking about. But every now and then, it does actually hit an atom, right? But we say that all of this is the material, right? Every now and then, it does hit an atom. Each of these atoms have electrons in various energy levels, which by nature of being charged particles interact with the electromagnetic wave that is the photon, right? The electrons interact with the electromagnetic wave. Makes sense. As the photon passes through the atom, the electric oscillation of the photon sets the electrons into vibrational motion, as would be expected of charged particles in an electric field. You probably are somewhat familiar with what I'm talking about from your Physics 2 class. If the frequency of oscillation that the electrons were just set into matches the resonance frequency of the electrons, then the photon is absorbed, and its current journey through the material is complete for that given photon. In other words, it's not completely re-emitted immediately after. The atom, as per energy conservation, would then be at a higher energy state, the energy gained by the atom being equal to the energy of the photon, right? So that's if the frequency of the photon matches the resonance frequency of that atom. If, on the other hand, the frequency of oscillation that the photon caused the electrons of the atom to be in does not match the resonance frequency of the electrons, a much more common scenario, then the photon is not permanently absorbed by the atom. Instead, it's just immediately re-emitted. Or if you want to think about it in these terms, you can, that it's rejected. and continues on through the material. This process of temporary absorption, oscillatory trial period of the energy, and immediate re-emission, because it's not the resonance frequency, this process takes some time. It slows down the journey of the photon. So the number of atoms that a photon runs into, on average, determines its speed through the material. And the number of atoms that a photon runs into for a given material depends on the wavelength of light. Generally, light of longer wavelength has a greater speed through materials than light of shorter wavelength. This makes sense when you think of light as a wave traveling through empty space with the occasional atom in its way. Longer wavelength means the light is not sweeping the space in front of it as rapidly, and thus is not as likely to hit an atom and be slowed by its interaction. It's traveling closer to a straight line. So it's, like this would be a dramatic opposition to something like that. Here, any atom that's in this, space, it's going to hit, whereas this one, it's not as often it's not sweeping left and right as often, so it's not going to run into atoms as much as the higher frequency photon. So when we look back at refraction, we see that the angle at which light is refracted depends on the index of refraction for the materials. So that was Snell's law, right? N1 sine theta 1 is equal to N2 sine theta 2, where the index of refraction N, we just learned, is defined by the speed of light through a material, right? So we also learned about index of refraction and that it is C over V, V being the speed of light through the material. So now we have a better idea of speed of light through material. If the speed of light through a material depends on the wavelength of light that we're talking about, then the index of refraction N of a material must depend on wavelength as well. And furthermore, the angle of refraction must depend on the wavelength. In other words, if the whole reason refraction happens is because the light changes speed as it passes from one material to another, then the amount that it refracts depends on the wavelength of light, because the wavelength of light really is what is determining the speed through the material. This is what is known as dispersion. Wavelength-dependent refraction. Dispersion is what causes white light, composed of the full spectrum of visible wavelengths, to be separated into color bands when refracted through a prism. Longer wavelengths mean faster speed through the prism, which means less refraction, less bending of the light. Let me paste this image in here while I'm talking, so you can look at that. Familiar thing, maybe. And I've frozen up. There we go. All right, where was I? Yeah, so this would correspond to red, is what we were just saying. I'll say it again. Longer wavelength means faster speed through the prism, which means less refraction, less bending of the light, and that's red, right? Isn't bent as much. Smaller wavelength means slower speed through the prism, which means more refraction, more bending. This is the more wiggly one, right? So it's more likely to run into atoms in this material. And so it's more likely to be slowed down, and so therefore it bends more. So that corresponds to violet. And you can read in your textbook a very detailed breakdown of how dispersion causes rainbows and also what causes double rainbows. I think that's very interesting, but it's not essential content, so I'll leave it to you to read in the textbook, but it's super interesting.